recently began to consider applying fundamental principles to multi-particle systems, systems that contain distinct pieces that can interact with each other within the system. We said that in some cases we can associate with those interactions a potential energy. Today we're going to see how this is so for interactions described by Newton's universal law of gravitation. Let's start by reminding ourselves that this law of gravitation tells us that when we have two objects, say mass 1 and mass 2, then we know the magnitude of the gravitational force on mass 2 by mass 1 is proportional to the product of the masses and inversely proportional to the square of the distance between the masses, where the distance is the magnitude of the relative position vector r. We remember the vector r locates mass 2 with respect to mass 1. The direction of the force is attractive and points opposite to the direction of the unit vector we form from the r vector. So we can express this direction of the force as minus r hat. Finally, we remember that gravitational forces are reciprocal, so that we know there is a corresponding gravitational force on mass 1 by mass 2, which is equal in magnitude and points in the opposite direction. So we can express this by writing the force of gravity on 1 by 2 as just minus the force of gravity on 2 by 1. Now, in preparation for applying the energy principle, we'll choose our system to contain both masses. So we're interested in the work done within the system by these forces as the masses move. Let's consider first where the masses have small displacements, delta r1 and delta r2. Small here means let's consider that the gravitational forces are approximately constant during this. So we can calculate the work done by these forces inside the system. First, there's a work done by the gravitational force on mass 1 as it displaces by delta r1. Here, that's just the scalar product of the force of gravity on 1 by 2 and the displacement delta r1. There's also, in general, work done by the gravitational force on mass 2 as it displaces by delta r2. That's just the scalar product of the force of gravity on 2 by 1 and delta r2. The total work is the sum of these. Now, we can use reciprocity to rewrite this term, and we can factor out the common force term because the scalar products obey this distributive property. Let's focus on the term delta r2 minus delta r1. We can expand and rearrange, and using a few steps of algebra, and we can see that this term is just the final relative position vector, and this term is just the initial relative position vector. So delta r2 minus delta r1 ends up just being equal to the change in the relative position vector delta r. So if we resketch our problem in these terms, we have that the total work on both masses due to the entire gravitational interaction can just be viewed as the scalar product of the force of gravity on 2 by 1 with the change in the relative position vector delta r. This is all still inside the system, so let's use our definition of the change in potential energy as the negative of the work done. So we write this down and use Newton's universal law of gravitation to write out the force of gravity on 2 by 1. And so we have this expression. Now let's emphasize here that delta r vector, the change in the relative position vector, need not be parallel to the r vector or r hat. However, when we take this scalar product, we end up with the change in the magnitude of r. We can write this as delta r with no arrow symbol, and we have in mind here that delta r positive means the distance between the masses is increasing, and delta r negative means the distance between the masses is decreasing. This all means that in finding delta UG, we only care about the changes along the directions radially toward or away from the relative origin, which here is the location of mass 1. So this is our result for small changes. But what if we have large relative changes in position, say something like this? Well, clearly we would have to break up the path into segments where we could compute the work on each segment using this expression and then adding everything up. In the limit of small displacements, this summing up would be an integration. The integration would be only along the radial direction. We can think of the magnitude r as the coordinate along the radial direction, and the differential dr describes changes. Dr would be positive as r increases if relative motion causes mass 2 to move further away from mass 1. So let's do this integral, and we end up with this result, which we evaluate between the limits. And when we evaluate this integral, we get this final result. Now recall, delta u means u final minus u initial. So we see that by comparison, we can find the expression for u sub g, the gravitational potential energy associated with Newton's universal law of gravitation. Interestingly, it's negative. We'll discuss more about that later, but for now, let's emphasize here that what's directly relevant physically is the change delta UG. Let's see if this expression gives us a sensible change in the gravitational potential energy by trying this example. Consider two stars, where initially they're separated by r sub I and both at rest. Moreover, assume nothing else interacts with these stars. Physically, we know that gravitational attraction will cause the stars to move closer together. Moreover, after some time, they will look something like this: closer together with a smaller separation, r sub f, and now with both having some non-zero speed in general. Let's write down the energy principle for this, where we choose both stars in the system. Then our energy principle looks like this. Delta E, the change in system energy, is 0. This is so because the stars are not interacting with the surroundings, so no work from the surroundings occurs, no transfer of energy into or out of the system of both stars. However, inside the system, we know that the stars interact with each other. So delta E has two main terms: delta K total, the total change in kinetic energy of the stars, and delta UG, the change in gravitational potential energy. Now, as we said, the sum of these changes must be 0. And moreover, we see that delta K must be positive. This is so because the initial kinetic energy of the stars is 0. They're not moving. But later, the stars are moving, so the final kinetic energy is non-zero. So final minus initial of the total kinetic energy gives us something that's non-zero and positive. Now, if that is so, then this must mean that delta UG, the change in gravitational potential energy, must be negative. Let's see if that is so. Because the stars are closer together in the final position than in the initial position, r sub f is smaller than r sub I. If we look at this factor, 1 over r sub f minus 1 over r sub I, this term is positive. However, the overall minus sign makes delta UG negative. This is as we expect, so this is sensible. Let's do an example that involves numbers to gain some experience. We are showing here a problem of a binary star system containing two stars whose masses we know. And initially, we know the stars' separation distance as well as the speeds of both stars. Sometime later, we know the separation distance. In this case, however, in this final state, we only know one of the star's speeds. This problem asks us to find the speed of the other star. To read through the details, you may wish to pause the video for a moment. Now, as a side note, our interstellar neighbor, the Alpha Centauri binary star system, that is located at a distance of approximately 4 light years from us, contains two stars labeled A and B, whose masses are close to what we have here. Now, for this problem, there are many different ways to sketch a picture of the motion situation, since we're not given specifics about the star's positions or velocities. Here's one possible sketch showing initial and final states. We don't really even know enough here to sketch in the trajectories of the stars between these states. Nevertheless, let's boldly push on and start from the energy principle. Let's make the choice where both stars are in the system. Here's the energy principle for this. Notice we have no agents in the surroundings interacting with our multiparticle system, so no energy transfer between the system and surroundings. Thus, delta E of this system is 0. But there are still non-zero energy changes within the system. the change in the total kinetic energy of the system, and the gravitational potential energy change. Let's calculate the potential energy change. It's U final minus U initial, and we can use our result for the change in the gravitational potential energy here. When we plug in all the numbers, we obtain this result. Now notice we find the result is negative. This means there is a loss. Where did that change in gravitational potential energy go? In this case, it all went into increasing the total kinetic energies of the stars. This must be the case because the sum of the total kinetic energy change plus the change in gravitational potential energy must add up to zero. It's good to keep in mind that, in general, potential energy changes can be shared by all parts of the system. We need to use the energy principle to tell us the specifics of the shared energy, in the case where one or both stars gain kinetic energy. So let's do that. First, for star B, we can use the information in the problem statement to find delta KB. Working that out, we see that star B gains kinetic energy. Now let's put this into the energy principle and we can solve for the change in kinetic energy of star A. We can see here that this is also positive, so the loss of potential energy of the system is shared by both stars as gains in their kinetic energies. From this we can find the final kinetic energy of star A, and then from this the final speed, which answers the question we posed in the original problem. Before we conclude this lecture, we'll make one final note about how changes in potential energy may be divided up within a system. There are cases where the lion's share of the changes to potential energy may be allocated to only one part of a multiparticle system. We saw an example of this in the case of the ball dropped near the surface of the Earth. The change in gravitational potential energy was negative, indicating a loss of potential energy of the Earth ball system. And we saw that was accounted for almost exclusively by the gain of kinetic energy of the ball. We said that was so because the gravitational interaction hardly affects the Earth, so there is essentially no change in the Earth's kinetic energy. So in this instance, the loss in potential energy in the Earth ball system shows up almost exclusively as a gain in the kinetic energy of the ball. This can happen with the more general form for gravitational potential energy. And for the same reason, when very large differences in mass are involved. Say, instead of considering two stars, we have instead one star and a very much less massive comet interacting. Then, while both feel the same magnitude of gravitational force, the gravitational force of the star acting on the comet can have an enormous impact on the comet's motion, can cause a big change in kinetic energy, whereas the same size force, same magnitude of force, the gravitational force of the comet acting on the star, hardly affects the star's kinetic energy. So, when the system potential energy changes, the energy gain or loss from the change shows up almost exclusively as the change in kinetic energy of the comet. Just make sure you don't fall into the trap of assuming automatically that the potential energy change always shows up in only part of the kinetic energy of a multiparticle system. It would have been a mistake to do this for our binary star system. The bottom line is, when we apply the energy principle for a multiparticle system, start by keeping track of all terms, all the changes in kinetic energies for each part, all the changes in potential energy. Then, if you decide to neglect one or more terms, make sure you understand explicitly why this is the case for the motion situation you are solving.